Welcome back to our short course on hypersonic aerodynamics, basic and applied. We're in the second session of the second day, talking about some applications of fundamental concepts that were covered in yesterday's session. At the end of the first session, I showed some pictures of the flow over a Mach 41 cone. And the key point that I brought out there was that the shock is pressed very close to the surface, and the boundary layer is very large. I want to continue with that and talk about the implications that that picture has and that flow physics has for the design of hypersonic vehicles. Yesterday you had a fairly extensive discussion of hypersonic viscous flows, and I want to touch on some of the key points that will be necessary for today's talk. As those of you who are familiar with the boundary layer concept know, there are a variety of parameters that we use to characterize a boundary layer. We characterize a boundary layer based on its frictional effects and its heat transfer effects, and also the way it interacts with the rest of with the free stream flow, or the inviscid flow sitting above it. And in order to evaluate that, the most convenient parameter is the boundary layer displacement thickness. Just looking at the equation which describes the boundary layer displacement thickness for a hypersonic flow, a couple of features become obvious. One, the displacement thickness scales inversely with the square root of the pressure ratio across the shock wave that's sitting above that boundary layer. Now, yesterday you learned about the tangent wedge method. You can think about this pressure ratio as being the pressure associated with a shock that would correspond to the inclination of the surface where we're evaluating the boundary layer displacement thickness. In other words, the boundary layer displacement thickness is very sensitive to the strength of the shock. Stronger shock, higher pressure ratio, squeezes down the boundary layer gets thinner. What that suggests even more, and yesterday you heard a little bit about interaction theory. It says that in hypersonic boundary layers, not only do we have thick shocks, but we have thick shocks which interact with the boundary layer. Now, consider the front surface of a hypersonic inlet, the forebody of a NASP. The very, very front leading edge has a boundary layer, and that boundary layer has some slope because the boundary layer is growing. And let me reclaim a pen from someone. Thank you. And if you picture that boundary layer, that'll be the flat surface. Let me make sure we can draw. And that boundary layer is growing along the surface. Now, even if the surface that we're looking at is at 0 degrees angle of attack, the boundary layer will appear to have an effective displacement, and therefore an effective angle of attack, or effective surface inclination, for the free stream flow. Now think about what that does to the shock. The shock wave will see what it thinks is a blunter body, or a blunt body in this case. And so we'll get a shock wave that responds to the curvature of the boundary layer displacement. Now remember that the strength of the shock wave sets the thickness of the boundary layer. Well, the thickness of the boundary layer is setting the strength of the shock wave. Thicker boundary layer, more curvature in the boundary layer, looks like a blunter body. Stronger shock, higher pressure ratio, thinner boundary layer. It's a strongly coupled problem. And that's what we mean when we talk about the strong interaction regime. Now, farther downstream on a hypersonic vehicle, if we continue this picture off the lectern, we'd come to a point where the boundary layer slope is relatively insignificant. And we can approximate the boundary layer slope as being about equal to the surface inclination. And once we get to that portion, the boundary layer slope is no longer augmenting the strength of the leading edge shock. And when that happens, we're in the weak interaction region, in which the shock pressure ratio sets the boundary layer thickness, but the boundary layer doesn't really interact strongly with the shock. Now, think about the implications of that, about this. If I take this picture, and we'll be seeing some dramatic realizations of this. If I take this picture, and remember this is supposed to be a surface at 0 inclination. Now think about what happens if I crank this surface up to some inclination. So I'm going to rotate the page. So now the incoming flow is at some angle. Well, you know that if you have a wedge at angle, you'll get a stronger shock, and the stronger the angle, the stronger the shock is likely to be. It means a higher pressure ratio. Higher pressure ratio means a thinner boundary layer. Now think of what that means in the context of the picture I showed of that thick boundary layer. As we crank up the surface inclination, we can squeeze down the boundary layer. In fact, the boundary layer height can be very sensitive to the surface inclination, and therefore very sensitive to the angle of attack of the vehicle. So one of the first things we worry about in the boundary layer problem is the sensitivity of the boundary layer to the flight conditions. Now, going through the extensive literature of boundary layer theory, many of these conclusions are things that you saw yesterday. Several things come to mind. As I said, positive angles of attack reduce the boundary layer thickness. At very, very high Mach numbers, the boundary layer thickness can become insensitive to Mach number. But bear in mind, the general rule of hypersonic boundary layer theory is that the boundary layer thickness scales with the square of the Mach number. So higher Mach numbers, thicker boundary layers. Boundary layers will tend to displace the bow shock off the front of the vehicle, off the surface of the vehicle, and that could be substantial if that boundary layer is thick. It was mentioned yesterday that wall cooling will tend to reduce the size of the boundary layer. And something that we'll be talking about later on, and that is that by and large we can assume that especially in the upper end of hypersonic flight, above about Mach 15, the boundary layer will be mostly laminar. And that's something that we're not used to dealing with in the design of aerospace vehicles. Now, you may recall yesterday in the discussion of strong interaction theory, a parameter was introduced called the interaction parameter. That interaction parameter is used to characterize whether we're in that strong interaction regime or the weak interaction regime. In other words, are we in the regime where the boundary layer and the shock are communicating back and forth between each other, or are we just in the regime where the shock dictates the thickness of the boundary layer? Let's look at how that interaction parameter will scale on a typical hypersonic vehicle. Generally, it's assumed that if the interaction parameter, chi bar, is greater than 3, we're in the regime of strong interactions. Now, that's a rule of thumb. That's not a fixed number. And some people will say greater than 1 means we're strong interactions. But we can pick that value, chi bar greater than 3, to represent the cutoff point where we have to start worrying about these extra boundary layer considerations, strong interaction theory. Remember that chi bar is defined as being inversely proportional, and there should be a cube of Mach number on this. That's a mistake. Inversely proportional to the square root of the Reynolds number. And remember, Reynolds number scales linearly with the dimension. So what this is really saying is that chi bar scales inversely with the length parameter on the inlet. In other words, a large value of chi bar means you're very close to the leading edge. And as chi bar gets smaller, you're moving further away from the leading edge. All right, let's look at some typical numbers. If we assume that chi bar 3 is the division between strong interactions and weak interactions, we can calculate values of chi bar with two basic assumptions. One is a cold wall. And I think for this one, we assume that the wall would be kept at about 1,000 degrees. And this one is an insulated wall, an adiabatic wall. The strong interaction regime at Mach 5 is, as you see, a very, very small value, 0.001 meters from the leading edge. In other words, once you get past this region, you're in the weak interaction regime. Well, let's look what happens as the Mach number increases. By the time we get to Mach 15, the strong interaction regime on the cold wall is about ½ a meter. By the time we get to Mach 20, it's almost 2.5 meters. By the time we get to Mach 25, it's grown dramatically. Remember, it's scaling with the cube of the Mach number. So by Mach 25, 8 meters worth of our forebody is in the strong interaction regime. And if we've got an insulated wall, the numbers are somewhat less severe, but the same trend is evident. The first thing that this tells us is, for a hypersonic vehicle, we definitely have to worry about the effects of strong interactions that we saw yesterday. Now, what do the boundary layer profiles look like? This is another thing that we have to worry about. In general, hypersonic boundary layers are not only thick, but they show enormous thermodynamic gradients. And you saw that yesterday, the boundary layers get extremely hot, and that's because all that kinetic energy is being dissipated in the boundary layer. That means that the temperatures are very high. That means that the densities are very low. And that introduces very, very strong gradients. Even if you cool the wall, even if you have some magic cooling system which is keeping your wall at some temperature below its melting point, you can still experience very, very high temperatures just slightly above the wall. Another key point, though, and that in some ways makes the realm of hypersonic boundary layers easier than any other boundary layer theory, is that because the temperatures are so high, the densities are very low. And that means that the displacement thickness is approximately equal to the 99% boundary layer thickness dimension. Now, for those of you who are familiar in boundary layer theory, you know that there are two ways that we can define the height of a boundary layer. One is with the displacement thickness, which is the effective thickness, the effective displacement that a uniform stream sees as a result of the presence of the boundary layer. And then there's the 99% thickness. And the 99% thickness is usually defined as being the point where the profile of the boundary layer is at 99% of the free stream values. And one of the difficulties in lower speed boundary layer theory is that these two values are usually very different. Right? At low speeds, the displacement thickness can sometimes be 10% or less of the 99% thickness. And you always have to be careful which one of these two you're talking about. Well, because of the low densities inside the hypersonic boundary layer, these two concepts really merge. So we can talk about boundary layer thickness, and we can jump interchangeably between the 99% thickness and the displacement thickness. If the boundary layer is laminar, by the way. If it's turbulent, this is less of a certainty. Okay? Another thing, when we calculate the momentum thickness, that's the effective lost momentum in the boundary layer, we find that in the hypersonic limit, it comes pretty close to 0. Why is that? Well, once again, temperature is so high, density is very low in that boundary layer. There's almost no mass flow moving in that. There's almost no mass in that boundary layer, so there's almost no momentum associated with it. That's very significant for the hypersonic engine, because if the engine is swallowing that boundary layer, it means it's taking in a region which has very, very little mass and relatively little momentum. Okay, let me show you some typical calculated profiles. And by the way, these profiles are not calculated with any fancy CFD. They're calculated using similarity solutions. And in fact, they're based on similarity solutions that were done in the late 50s by Cohn and Rashotko at NACA. This is the boundary layer mass flux. This is 10 meters down a flat plate at Mach 25, conditions of 50-kilometer altitude. Various other parameters are selected here. Prandtl number 0.75, which you don't really have to worry about. The key thing I want to show you is, you notice the mass flux in the boundary layer is effectively 0. There's almost no mass flux here. This looks like a corner in the profile. In fact, it's not. If I plotted this on a larger scale, you'd see that this is continuous. It's just in the scale that I plotted it, it looks discontinuous. But that shows you the magnitude of the gradients associated with the boundary layer. The boundary layer in hypersonic flow is very sharply defined. Velocity profiles also, once again, see extremely sharp gradients. This is same conditions, Mach 25, 50 kilometers. Imagine that this is sitting next to the wall. We go effectively from 0 meters per second to 1,000 meters per second in a space of 0.4 meters. Now, if we calculate using the simple flat plate theories that are developed, we can actually, without jumping into computational solutions, we can calculate what flat plate boundary layer thicknesses will be. And again, we see the same problem that was alluded to earlier. And that is that as we go up in Mach number, boundary layer thickness can become an appreciable fraction of the total shock layer. Right? These are some numbers which I've calculated for Mach numbers ranging Mach 15, Mach 20, and Mach 25 at different altitudes with different angles of attack on the flat plate. Some of them have cooled walls. In the last case, I don't have a cooled wall. It's an adiabatic wall. And what this shows is along that flat plate at various lengths, 5 meters along the plate, 10 meters along the plate, and 30 meters along the plate, you see the displacement thickness, and you see the height of the shock above the surface. And the key thing to note is that at the lower Mach numbers, even at 30 meters, the displacement thickness is a relatively small fraction of the shock thickness. But once you start getting up to the higher Mach numbers, I mean, for instance, when we're at Mach 25, see the displacement thickness is an appreciable portion, an appreciable fraction of the total shock layer. And the engine will either divert that flow or it will have to swallow it and deal with it. Now, one indication, this is a cooled shock layer. This is flying at Mach 20, 50 kilometers. This is flying at Mach 20, 40 kilometers. And one thing you notice is that the boundary layer thickness is very, very sensitive to altitude. It's also very sensitive to angle of attack. So changing your flight conditions, changing the angle of attack of the vehicle can have a dramatic impact on the nature of this flow. And remember, this flow is being dumped into the engine. So if you've designed an engine to swallow this sort of flow, you might be surprised to find that when you change the flight conditions, you're swallowing that sort of flow. And that's something that the hypersonic vehicle designer must be prepared to deal with. Now, how do you do that analysis? Well, there are a variety of schemes, but ultimately, they always seem to get back to computational fluid dynamics. And you recall that I mentioned that we simply don't have sufficient ground test facilities to adequately reproduce the hypersonic flight regime. And so a lot of work is being devoted in the NAS program and with associated hypersonic efforts to extending our knowledge of CFD and developing existing CFD packages that can be adequately used for analyzing hypersonic vehicles. This is just one view graph which shows various codes that can be used in studying the performance of a hypersonic engine. And the one thing I want to bring out is something that I've been saying since early this morning, and that is that the hypersonic engine must be considered in relation to the rest of the vehicle. So in this case, you see various different codes being applied, two-dimensional Navier-Stokes, boundary layer codes being applied, different codes being applied to the cowl leading edge, parabolized Navier-Stokes code here being applied to the nozzle. And each of these must be interacting with the other. It's impossible to consider what the engine is doing without knowing what's going on in the inlet, just for the purposes that I've shown, just for the reasons that I've shown. And some of the primary codes that are being used in the industry now, this is actually admittedly a bit dated. There has since been some other codes developed. NASCRIN, NASSTAR, SCAMP are all codes that are currently being used in the industry. Unfortunately, there isn't that much validation data available. Holden at CalSpan has done a variety of validation cases. He's got some test cases of Mach 14 flow over compression ramps. Aside from that, there isn't all that much flight test data. And that would be it would be nice to see some more flight test data before we actually start flying hypersonic vehicles. I've also included in the notes, and I won't dwell on that, but you've got a table of various models, and those models are listed by their names, and the names of the author, the references or the companies or the centers at which they were developed, the algorithms of those cases, and then what those things can be used for. And again, I won't dwell on those, just to say that if you're interested, you might refer to your notes. This view graph, these notes are admittedly about, now they're about a year out of date. But these are still standards that are being used. And new things are being developed all the time. Now let me just show you some numbers when you do a tip-to-tail analysis. You see some very interesting features. One thing to notice is that along this vehicle, all right, this is the undersurface of a hypersonic vehicle. Condition 0 are the free stream conditions. 1 is behind the first shock. 2 is at the entrance of the engine. 3 is supposedly the end of the combustor. 4 is the inlet to the nozzle, and then we have the exit plane. Notice that across the shock, there isn't much of a velocity change. But notice also that the Mach number changes dramatically. That's one of the key features that we see in hypersonics. Under the flow conditions that something like a hypersonic vehicle will see, in general, changes in Mach number translate into changes in temperature, not in changes in velocity. That's very convenient, because it means that even though we might drop the Mach number in the engine down substantially from the flight Mach number, the velocity of the flow inside the engine is probably pretty close to the velocity outside the vehicle. That's a good rule of thumb. Notice also that in this particular instance, great pains have been taken to increase the pressure inside the engine, in this case to about 3 atmospheres. That might be a little bit high. This is something that we'll be talking about later. We'll see that for the combustion system, you really have to provide pressures on the order of about an atmosphere, or at least a substantial fraction of an atmosphere, if you want the combustion system to proceed to completion in a reasonable length engine. Question in the back?
Velocities for station 3 and 4 are supposed to be 23 and 24,000?
Actually, I believe they are. I think that's a misprint. I believe they are. I was just looking at that as I put that down. That would be much more reasonable. Yeah. Yeah. Thanks for pointing that out. Very quickly, the validation data that's used, and this data is old, but it's about the best we have. Although there is a lot of data being produced with the NASP program now and NASP inlets. A lot of it is in the classified literature, unfortunately. But these are the Mike Holden solutions, 15-degree compression corners at Mach 14. And many of the codes have done a reasonably good job at reproducing these flow fields. And we actually have a great deal of confidence in the code's abilities to predict what a hypersonic vehicle will actually be seeing. Now, what's one of the first questions you ask about a boundary layer? I mean, those experts in boundary layer, I say, hey, I've got a boundary layer on the vehicle. First question you're going to ask is, well, is it laminar or is it turbulent? Because the whole nature of the boundary layer depends on whether it's laminar or turbulent. And you know that for low-speed applications, we have pretty good ways of estimating when the flow will transition from laminar to turbulent. So they're semi-empirical, but by and large, we have a pretty good feel for when that occurs. One of the first problems we run into in hypersonic flow is we don't know the answer to when the flow transitions. Let me show you a plot of transition. The symbols on this plot represent a variety of flight data points, and I think they're mostly taken from X-15 tests. I think some of them are free flight tests. I don't know the source of all of them. But the key point that I want to bring out in this plot is, well, two key points I want to bring out in this plot. One, at lower speeds, we're used to thinking that as the Mach number increases, the transition Reynolds number decreases. And in fact, if you look at this side of the plot, from Mach 0 down to Mach 4, the wind tunnel data indicates, indeed, that the transition Reynolds number is decreasing with increasing Mach number. Notice what happens at the higher Mach number. When the Mach number begins to increase, once you get around above about Mach 5, increasing Mach number actually increases the transition Reynolds number. In other words, it delays the onset of turbulence. The higher the Mach number, the longer the path length over which the boundary layer will remain laminar. That's the first thing I want to bring out. And notice, of course, that this thing is plotted on a logarithmic plot. So it turns out, in fact, that this line, this wind tunnel data correlation, scales almost with the 4th power of Mach number. So the delay in transition that is associated with higher Mach numbers is very, very sensitive to the flight Mach number. Something else I want to point out in this plot. As you can see, this solid line is the wind tunnel data correlation. Notice what a great job it does predicting the flight test. Not a very good job at all. Invariably, the flight test data gives us transition Reynolds numbers that are higher than the wind tunnel numbers. And there are a variety of theories that have been proposed for this. Tunnel interference, the fact that wind tunnel models tend to be smaller, so they tend to be blunter. If you have bluntness, that tends to induce favorable pressure gradients, which in turn tends to delay transition. But the key point is that you always have to be very careful trying to apply wind tunnel data in predicting transition on a hypersonic vehicle. Always be skeptical about that. And any correlation that you're handed, there are a variety of correlations that are out there. I've used some. Dr. Bocut has done his own correlations. And any of those correlations, including our own, you should treat with a certain amount of suspicion. And this is one of the key points that I think will come out of hypersonic flight testing. We've got to do some measurements in transition, or else we have no idea what's going in the engine. Yeah?
Is there a possibility of relaminarization on hypersonic vehicles?
Actually, we'll see that you almost have the opposite problem, which is you almost have the problem of not being able to get the flow to go turbulent when you want it to. One of the things that this indicates is that it becomes more and more difficult for flow to become turbulent, and we'll talk about some fundamental reasons for that. So it's actually relatively easy to keep the flow laminar. For a variety of reasons, you would like the flow to be laminar on the forebody, less frictional effects. You'd like it to be turbulent inside the engine. So there's been discussion about how you try to trip that flow. Imagine, though, a boundary layer trip which has a Mach 25 flow passing over it. One would suspect that the boundary layer trip wouldn't survive very long. So
Well, once it becomes turbulent, is there ever a chance that it would go back to laminar at higher altitude?
that's a good question, and I don't know the answer to that. I'm not sure. I think most of the schemes that have been proposed for relaminarization at lower speeds probably wouldn't work at the higher speeds, but I'm not sure. You probably, I don't know. Kevin, do you have anything to add to that? Or?
I'll talk about it.
Okay, great. We'll see some discussion about that later on. Okay, let me give you one set of data and one indication of how flight tests of some these are actually free ballistic flights, but it points us in the direction of what transition does on a hypersonic vehicle. This is data that was done by a gentleman named Sheets in the mid-70s. Basically, he took a variety of models, mostly conical models, at various angles. He's got 3-degree models, 5-degree models, 6.3-degree models. And he flew them in a ballistic range. He took photographs of them and measured the transition points on these models. When he did that, you know, I'm not sure. I don't think so. I
he
don't
had
think
some
so.
angle of attack on him then.
I think he was basically trying for a ballistic flight. So I don't think there was much of an angle of attack. I think it was basically a straightforward ballistic flight. I don't think they were spin stabilized. What he plots up as data, he finds that, again, transition Reynolds number increases as Mach number increases. He also found that the transition point is very, very sensitive to the geometry. In other words, when he changes the nose radius, when he changes the cone angle, he gets a very different plot of the transition Reynolds number versus Mach number. Now, he also came to another interesting realization, which was when he stopped referencing his conditions to the flight Mach number and started referencing to the conditions of the local Mach number, that is the Mach number on the surface of the model, all of his data collapsed onto one line. And in fact, this line scales approximately with the 3.7 power of Mach number. This is what I like to use as data for transition. But again, there's a warning. This is data which was derived on small cones. And whether you can apply this to a more complicated NASP geometry is anyone's guess. And because of the sensitivity to Mach number, we're talking about Mach number to almost the fourth power, small changes, if I had a different set of data and I made a small change in that, I could get a dramatically different prediction on where transition will occur in the vehicle. Using that data, though, we can estimate approximately what regimes will be in for the boundary layer coming in on the undersurface of a hypersonic vehicle. What I have shown here is a plot of altitude versus Mach number. And on this plot, I've superimposed 3 trajectories which are calculated for constant dynamic pressure. This isn't to suggest that that's the best way to fly a hypersonic vehicle, but it'll give you an indication of what we're talking about. Generally, we can expect that a hypersonic vehicle, in order to provide sufficient performance in the engine, is going to be flying at dynamic pressures higher than about 1 atmosphere. So we're probably talking about a vehicle that's in this range right here. Notice that below about Mach 10, the transition point, well, let me restate that. I have these 3 dashed lines which indicate where the transition occurs in the vehicle. The first dashed line is for transition at 10 meters, second dashed line is for transition at 30 meters, and the third dashed line is for transition at 100 meters. Now picture a vehicle which is about 30 meters long. What this is saying is that if I'm 30 meters long and I haven't yet hit that dashed line, my flow is completely laminar. On the other hand, if I'm 30 meters long but my transition occurs at 10 meters, that means that the flow coming in the engine is mostly turbulent. So you see what this is telling us. Right? Looking at this plot, we can basically see the following behavior. Below about Mach 10, we can expect for a 30-meter long vehicle that the flow coming into the engine is primarily turbulent. We can pretty well guess that. Above about Mach 17 or so, the flow coming in the engine is probably going to be laminar. In other words, over the entire surface of that vehicle, the boundary layer will probably be laminar. In between, anybody's guess. Now, a lot of the work that's being done in computational solutions has looked at turbulence modeling and trying to do transition predictions. We've made a lot of advancements in that, but we still have a lot to go in that. Another issue that we have to worry about, and that is the following. I told you that one of the critical keys that we worry about in the scramjet is the combustion process. It turns out that combustion is extremely sensitive to the thermodynamic conditions inside the engine. And actually, before I show this plot, let me show this plot. These are calculated combustion, and I think that's a few view graphs back in your notes. These are calculated combustion times required to reach completion in a hydrogen-air system. In other words, this is the time required to get, I think this is based on realizing 95% of your final combustion temperature. And you see several lines plotted as a function not only of temperature, but also as a function of pressure. Several key things to note. One, as I up the pressure, the time required for combustion drops dramatically. Two, notice that the increasing the temperature also tends to drop the time required for combustion. Third thing to notice, we talked about a reasonable rate, a reasonable combustion time required for a scramjet? Generally, we can guess that we've got to get that fuel to burn in at least about a millisecond, or thereabouts. Well, the millisecond line is right here, and I'll indicate that with the pointer. That tells us if we've got flow coming into the engine at about 1,000 degrees, or 1,500 degrees in that range, we have to be somewhere at some reasonable fraction of an atmosphere in pressure in order for that fuel to burn fast enough inside the engine. If we go with a lower pressure system, then we simply won't get reaction at a sufficiently rapid rate to be able to design a reasonable engine. So that means that the propulsion system depends on the inlet supplying flow at the right temperature and the right pressure, or the combustion simply won't work. Now, that's very interesting, because you might say, all right, well, I should have complete freedom in picking that inlet. Right? I should be able to design any shock system to give me the right pressure and the right temperature. But unfortunately, it doesn't work that simply, because the pressure and temperature across a shock are coupled. Right? If I pick a shock at a given angle, I know the pressure ratio, but I also know the temperature ratio. In fact, we can look at the coupling of that. This is a plot. This is assuming a two-shock inlet. And each of those shocks is generated by a 10-degree wedge. There's one 10-degree wedge and then another 10-degree wedge. This is a plot of altitude versus Mach number. Now remember, I said that we probably would like to be operating with about 1 atmosphere pressure coming into the engine. Well, this line corresponds to what would supply 1 atmosphere pressure. Notice what's happening to the temperature across that shock system. Right? We start out at 500 degrees being delivered to the engine, and we wind up with 3,000 degrees by the time we hit Mach 25. And that's probably too hot for hypersonic combustion, right? The hydrogen-air system will burn up to about 3,500 degrees. So if the air is coming in initially at 3,000 degrees, we're not going to see much heat release inside the engine. So that puts some very tight constraints in the design of that inlet. We have to be able to design an inlet which can supply those conditions appropriately. At the same time, we're really fighting nature. Okay. We're talking about the boundary layer. You notice, by the way, I'm posing lots of questions. I'm not giving you very many answers, because these are difficult problems, and not all of them are readily solvable. Another question that's not readily solvable is that of the boundary layer. What do you do with the boundary layer? There are basically two possibilities. One is you swallow it, and the other is you don't swallow it. If you don't swallow it, that means you have to divert it in some way. Now, there are some people who suggest that diverting the boundary layer is not a particularly good idea, because you'll lose some momentum. I mean, remember that flow doesn't have much momentum, but it has some. And it turns out when you do the analysis of a full hypersonic vehicle, the thrust is not all that much greater than the drag. And if you're losing momentum from that flow, you're losing some thrust. You've got extra drag on the vehicle is another way to think about it. And that in turn means that you're lowering that thrust drag margin even more. And that might be a penalty that you cannot pay on that vehicle. So it might not be possible to divert the boundary layer. Another problem is, if you're going to divert the boundary layer, how do you do it? Right? You might consider putting in a boundary layer duct to bleed away the boundary layer. Remember, though, yesterday you saw that the boundary layer temperatures can be enormous. So you've got to have some duct which can handle all that hot air. I'm not quite sure how you'd go about doing that. And there have been a lot of papers written in which people have shown the boundary layer about to go into an engine, and it gets bled off in a duct. Well, they never say how that duct will be designed, or what it will be made out of, or how it will be kept cool. You know, obviously, it will be designed out of some unobtainium, which can handle those high temperatures. You might argue, all right, we know how to handle boundary layer problems. On an F-16, for instance, we handle the boundary layer problem by just displacing the inlet below the fuselage of the vehicle. So the inlet doesn't swallow the boundary layer goes underneath the inlet. Again, you can't really do that. I mean, imagine what would happen if you tried to offset a hypersonic engine below the surface of the vehicle. You'd have some pillar or some pylon between the engine and the vehicle, and that pylon is going to be sitting in a very high Mach number flow, and it probably isn't going to survive very well. So that's probably not a viable option either. Suggestion has been made that you might be able to induce boundary layer diversion by introducing a pressure gradient in a spanwise direction. That is a possibility and has been demonstrated. Specifically, Leo Townend in England has shown that you can do that. But that also raises the question, if you've got pressure gradients which divert the boundary layer to the sides, it's probably also giving you non-uniform flow coming into the engine, and that might not be desirable. And whether you can effectively do this side diversion and not introduce detrimental non-uniformities, I think remains as a question to be seen. Other problems with the boundary layer. I mean, we've been talking about the boundary layer being very thick, not having much mass. It isn't clear what the chemistry of the boundary layer will be like. Can we get fuel to react with the boundary layer gas? That's not clear. There isn't much in the boundary layer to react with anyway. And the boundary layer will be extremely hot, probably above the equilibrium combustion temperature of the fuel. So that must be completely lost to the combustion system. If we don't know what state the boundary layer is in, laminar or turbulent, that also figures into whether we can get combustion in the boundary layer. We don't even know how the chemistry in the boundary layer couples in to the turbulence of the boundary layer. In fact, that's a real hot research question right now. How does the chemistry of a turbulent flow affect the level of turbulence, and how does the level of turbulence affect the chemistry? That's a big unknown. That's also a commercial advertisement for an area that we need more work in. As I said, large mass flow variations and sensitivities to flight conditions. You might design an engine which can swallow a boundary layer of known dimension. And the minute that vehicle goes off design, if it takes a little bit of angle of attack, if it changes its Mach number, that boundary layer thickness could change dramatically. And that means the amount of mass that's being swallowed to that engine could change dramatically. You could have order unity changes in the mass that goes into the engine just by changing the attitude of the vehicle, if you're not careful. And just a cartoon to indicate that, you've got this profile coming in off the forebody of the engine, and the engine has to, the forebody of the vehicle, and that engine has to deal with that profile if it's not being diverted. Okay. As we said, just by way of summary, boundary layer thickness increases with altitude. If you have a positive angle of attack, or if you have a larger ramp, you tend to reduce the boundary layer thickness. And that's, by the way, also very important. If you're designing the flow on a hypersonic inlet, you have to be very careful to remember that if the inlet is at some inclination angle, the boundary layer thickness could be very different than the boundary layer thickness on a flat plate. At large angles and even modest angles, the boundary layer thickness becomes inversely proportional to the angle of inclination. So in other words, the difference between a 5-degree inclination and a 10-degree inclination can be a factor of 2 in the boundary layer thickness. And that's an important thing you have to consider. Again, it displaces the bow shock. We talked about wall cooling effects. And our final conclusion is that at the high Mach number end, certainly above Mach 15 or so, the boundary layer will be mostly laminar. Below that, we don't really know for sure. OK, what is the effect of trying to swallow that boundary layer? Let's say we take the boundary layer into the engine. What does it do? Well, let me show you the simplest model that we can consider when we're dealing with swallowing the boundary layer. Let's think about a one-dimensional model. We've got two flows coming in. We've got this inviscid flow, which is the inviscid shock layer. You can imagine sitting out here. This is the engine. Sitting out here is the shock wave. And then there's an inviscid region beneath the shock wave. And then there's the boundary layer. And those two can be of comparable thickness. You've got this boundary layer flow, and you've got this hypersonic inviscid core. Well, in general, we like to think in aerospace engineering that the boundary layer is a detail that you add in after the fact. You do your inviscid flow calculation, you do your boundary layer calculation, you add it in. And sometimes, if you're ambitious, you do coupling between the boundary layer and the inviscid core. You might try to iterate between these two. Sometimes that isn't a stable converging process. But in general, the boundary layer is a detail that we add in later. That doesn't work in the hypersonic flow. And you can see that very clearly from some work that was done by 3 gentlemen in the 60s. Heavener, Heiser, and Bernstein were looking at mixing of different stream tubes in relation to subsonic engines. They were interested in the flow coming out the back of high bypass turbofans. And they developed a very elegant one-dimensional theory of what happens when stream tubes of different speeds encounter area changes. And they defined a parameter which they call the compound influence parameter. They gave it the symbol beta. And beta is a way of evaluating whether the compound flow behaves as if it were subsonic or supersonic or choked. Now let's go back to the model. Looking at that stream tube model again. We've got a very, very high Mach number flow in this inviscid region. We've got a boundary layer which starts out at a very high Mach number but drops down to Mach number 0 at the wall. Now look at this parameter. The parameter, beta, is summed over each one of those individual stream tubes. In the 2-stream tube model, we'd only sum over 2 stream tubes, the core flow and the boundary layer. Obviously, boundary layer realistically has a profile, and we might want to do more stream tubes. But we can illustrate the physics with just the 2-stream tube model. Notice that the beta parameter scales inversely with the square of the Mach number minus 1. If I have a very, very large Mach number, 1 over Mach number squared is a small number. If I have a very low Mach number, 1 over Mach number squared can become a very large number. So what that tells us is that a relatively lower speed stream tube can have a dramatic influence on the bulk behavior of the flow, even though it might even have a much smaller area than the high-speed stream tube. In other words, even if the boundary layer is relatively modest size, because of the sensitivity of the net performance of the flow to the inverse square of Mach number, that boundary layer can change dramatically the nature of the flow inside the engine. In other words, the way the flow responds to changes in area, or the way the flow responds to heat addition. Now, let's take an example. If we want to consider what happens inside an engine, there are a variety of ways to solve the problem. We can do a very, very complicated full-blown computational scheme, or we can seek out some simple baseline examples. And I'm going to take the latter approach, because we can illustrate most of the physics with some very, very simple combustor designs. The two combustor designs that are most often spoken about are the following: constant pressure design and constant temperature design. Now, let me tell you the advantage of constant pressure. If we have a constant pressure design, that means we have no adverse pressure gradients in the combustor. That's very good, because that means we're probably avoiding a separation of the boundary layer. We probably have very well-behaved flow inside that engine. How do we do that? Well, you know that we're going to be adding heat inside the combustor because we're burning the fuel. If we had a one-dimensional channel with heat addition, in the process of heat addition, we're trying to increase the pressure. So the way we offset that is to balance that pressure rise by expanding the area. And you can derive the equation to do that, and the one-dimensional solution is really quite straightforward, quite elegant. One way to think about the constant pressure combustor, by the way, is since there's no pressure gradient, there's no change in the velocity of that engine. So what that means is that all the energy goes into thermal energy. Now, of course, that thermal energy then gets converted to useful kinetic energy back in the nozzle, but it's a limit. And again, the advantage is with the constant pressure design, you avoid separation. And that's why most of the designs we talk about for engines, not only in hypersonic flow, but in all flight regimes, tend to seek constant pressure design. Now let's consider another possible design. That would be a constant temperature design. What's the advantage of a constant temperature design? Well, thermodynamically, I would like to accomplish my combustion at the highest temperature possible. That's just from the point of view of thermodynamic efficiency. So I might reason that the constant pressure design is really not the best way to go. From the point of view of thermodynamic efficiency, what I'd like to do is first initiate some combustion, get my flow up to some high temperature, and then continue the combustion at as high a temperature as I can stand in the engine. That, in a sense, is the other limit from the constant pressure design, because in that design, since we're taking it up to a high temperature and holding it at that constant temperature, all the energy goes directly into kinetic energy. You can almost think of that as a pre-nozzle. What's the disadvantage of that? Well, disadvantage is you now have pressure gradients, and you have to deal with flow separation. And so this might not be as viable an engine concept. Turns out if you benchmark these two designs, just one-dimensional models, the specific impulse, not surprisingly, of the constant temperature design is a little bit better than the constant pressure design. But the adverse pressure gradients are probably such that you would seek out the constant pressure design. It's just not, the improvement is not sufficient to be worth all the complications imposed by these two design criteria. Okay. What happens if we put a flow profile into a hypersonic engine? Several things. One of the things we find is boundary layer experiences very rapid heating, very rapid pressure rise, and after that, combustion stops in the boundary layer. So by and large, some simple models indicate that you don't get much energy released in the boundary layer. What that means is, if you want combustion to proceed, you're driven to a longer engine, which is a heavier engine, which is something that the airframe people don't like. Okay, I mentioned that there are a variety of other issues. One of the key issues associated with scramjet design is getting the fuel to mix. It turns out one of the most difficult problems in hypersonic flow and hypersonic engine design is getting the fuel to mix before it blows out the back of the engine. And indeed, this is a problem that comes right out of the fundamental flow physics. Let me give you a very, very good, simple, fundamental argument for why it is so difficult to get the fuel to mix. Many of you are familiar with the classic solutions of flow over a wave-shaped wall. It's one of the classic solutions in undergraduate textbooks. And you know that when that problem is solved, there are two separate limits that are considered. The first limit is the subsonic limit, and the second limit is the supersonic limit. Now, those two flow solutions have very, very different behavior, and that's why it's used as an example of the difference between subsonic flows and supersonic flows. You may well know that in the supersonic limit, if I have a wavy wall, and let's just think of this is a wall for now, I get pressure maxima, I'm sorry, pressure minima at the peaks and pressure maxima at the troughs. Now let's imagine, instead of a wall, let's pretend that this is some disturbance introduced in the flow. Think about what's going to happen. In subsonic flow, you've got pressure forces acting to increase the height of this disturbance and to increase the height of that disturbance. In other words, in subsonic flow, any disturbance is unstable. It tries to increase in magnitude. The amplitude of the disturbance will try to increase. And that means if I introduce a disturbance, I can expect it eventually to go nonlinear. Now, look at what happens in supersonic flow. In supersonic flow, let's just start off with a wavy-shaped wall. I get the pressure minima at the expansion surfaces and the pressure maxima at the compression surfaces. Now, once again, make the transformation. Instead of thinking about that as a wall, think about that as a disturbance that's sitting between two flows. And now those two flows are moving at a relative supersonic Mach number. So from the point of view of those flows, that disturbance might as well be a wall. Well, the maxima and minima of pressure line up on either side of those disturbances. In other words, in supersonic flow, there is no trend to amplify the magnitude of that disturbance. Now, indeed, the first thing you say is, all right, we know there's a famous theorem in incompressible flow. It's called Squire's theorem. It tells you if you calculate the stability of a two-dimensional flow, it turns out that the two-dimensional flow is the most unstable case. So if you show that it's unstable in 2D, then you know then you know that that's a limiting case for a real three-dimensional flow. This doesn't hold true in compressible flow. And the reason is, if you think about this wavy disturbance moving between two streams, right, there's always some oblique angle at which you can look at your disturbances between these two streams at which the relative Mach numbers will be subsonic. So in fact, even though the supersonic disturbances are neutrally stable in 2D, in three-dimensional there's always going to be some instability for any disturbance. But it's going to be much smaller than for the subsonic flow. And again, I want to emphasize, this comes out of the fundamental fluid mechanics. This is a fundamental law of physics that we've got to fight in order to get the fuel to mix. Right? Now imagine if one of these streams, let's say this side is the hydrogen fuel, and this side is the air. Right? Imagine what happens as these two are moving along. Well, disturbances don't induce mixing readily. So those two streams continue on their own merry way without mixing effectively, unless we do something to enhance the mixing. Other issues that we have to deal with. If the boundary layer separates, separation and heating rate can be a critical matter. The boundary layer is hot, as we've talked about several times. That can happen on the forebody, and it can be induced by combustion. Right? The boundary layer can provide communication from the combustor to the inlet. And if you're not careful, if you don't design the combustor correctly, you can actually induce separation all the way up on the inlet just through the act of burning fuel in the combustor. You've got to check the combustion rate. I'll hammer that point again. You have to have an adequately small reaction time. And that combustion rate is so sensitive to the thermodynamic properties that the inlet has to provide those correct properties. And that actually puts severe limitations on the trajectory of the vehicle as well. OK, let's talk about how you can go about enhancing the mixing of a supersonic stream, such as a fuel jet. There are, in fact, a variety of schemes, and we won't talk about all of them. There's been a fair amount of work done at NASA Langley, primarily by Phil Drummond, on looking at how you can induce mixing by placing various blunt bodies, shock generators behind the jet. A very novel scheme that came from Caltech uses a different approach. It's called the shock-induced vorticity scheme. The way it works is as follows. This is an incredibly elegant use of fluid mechanics. It's one of my favorite schemes. Many of you may be familiar with the famous Helmholtz equation. It's the equation of vorticity transport in fluid dynamics. If you're not familiar with it, don't worry about it. All I want to say about it is that the Helmholtz equation describes how vorticity moves in a fluid. And if you're familiar with that Helmholtz equation, you're probably familiar with two terms in that equation. Right? You're familiar with the vortex stretching term, and you're familiar with the viscous term. It turns out there is a third term in the Helmholtz equation, which is a vorticity generating term, which is usually neglected. And that's this term right over here. And let me tell you why it's usually neglected. When the Helmholtz equation is derived, you remember that vorticity is taken by taking the curl of the velocity. So in order to derive the Helmholtz equation, you take the curl of the momentum equation. And so you wind up with a curl of a remember the momentum equation has a gradient of pressure term. So you wind up with a curl of a gradient of pressure. And the math whizzes in the audience know, hey, curl of gradient, that's 0. So usually this term is dropped out. Well, it turns out that that's not strictly mathematically true. And the reason is that the momentum equation actually has gradient of pressure divided by density. And if the gradient of the density is not aligned with the gradient of the pressure, then the curl of the gradient of pressure divided by density is not 0. It is finite valued. In other words, the curl of the gradient of pressure over density gives you a finite value term, and that appears in the vorticity generation term. Now, what does that mean in terms of the physics of the situation? Well, let me give you the following flow scenario. Let me borrow a pen back. Sorry about that. Let's consider a fluid element. Let's make it a square element. And let's assume that there's a gradient of density in this element. So the fluid down here is more dense than the fluid up here. Now let's consider a misaligned pressure gradient. In fact, let's take a pressure gradient across the element. So we have high pressure here, low pressure here. Well, where is the center of mass of this element? It's going to be down here. Where is the center of pressure? Well, if the pressure is uniform, then it's going to be somewhere higher, somewhere up here. Well, what happens if you push on an element with a uniform pressure and the center of mass is down here? The element is going to rotate. You're going to induce vorticity. And in fact, this is a real natural occurrence. We see this all the time in the oceans. The deep oceans have density gradients. And when you have an ocean current, you can actually induce vorticity with this baroclinic term, this pressure gradient term. Now, aerodynamicists aren't used to worrying about this. We generally don't see this flow situation. But indeed, we can create this flow situation inside a hypersonic engine. That is use the following method. We inject a hydrogen jet into the air. Well, by its very nature, the hydrogen jet is going to be at a different density than the air. So there is a strong density gradient at the interface between the hydrogen and the air. How do you induce a strong pressure gradient? Well, the best way I know is with a shock. So you hit the jet of air with a shock. Notice that the shock pressure gradient is aligned with the plane of the shock. It's actually normal to the plane of the shock. The density gradient across the fuel is aligned with the surface of the fuel. That's a misaligned gradient. In other words, the action of the shock on that fuel jet induces vorticity, and it's been measured in the laboratory. It's been demonstrated computationally. That causes roll-up of the jet. What are the problems with that? Well, one problem is, of course, you need a shock. And shocks have losses associated with them. So this becomes an engineering game. Picking a shock which is strong enough to induce the vorticity and induce the mixing, but making sure it's a shock which is weak enough that you don't suffer strong total pressure losses and thus ruin the performance of the engine. Again, this is by no means the only concept. Other concepts that are being considered are mixing lobes, different injection schemes off the wall, injection schemes off the injectors. There's a lot of work being done in the field, and there's a lot of work that remains to be done in the field. Let me wrap up this section of the talk by asking if there are any questions on this, either from our audience or from our remote sites. If not, then I'll give you a taste of things to come in the next session. And that is, we're going to be looking at specific problems, key fluid physics problems associated with hypersonic vehicle design. Specifically, I want to look at problems associated with the desire to match the bow shock to the engine cowl lip. We'll see that that introduces some interesting design considerations. There's some interesting flow physics that must be dealt with. And there's some interesting work going on right now in the literature which addresses these issues.